Well, good morning to all of you, first of all. And I thank this high school, Messieurs dames, for having imagined this opportunity, this possibility, and this conference, okay? I think I just want to say a simple thing first. I mean, the relevant part of my education, curriculum and so forth is that I have been working for research in physics, theoretical physics, and so forth for about 5 years in England, in the United Kingdom. That is where I learned English, truly speaking the language. I was educated in Belgium, as I told Francesca. I am from the French-speaking part of Belgium, and then I grew up in a Flemish-speaking town in Belgium, so I had to learn Flemish. And I knew Italian because my mother is Italian. So at home, the mother languages, the mother tongues were French and Italian, so I had to learn Flemish, which is essentially Dutch, right? The thing they speak in Holland, and which is a Germanic language. And this already makes it rather easy to, learn English. The pronunciation especially, of course. And also the vocabulary and some grammar and so forth. But my level in English was rather medium, not exceptional at all. I wasn't very good at school, at high school in English. I learned it in the United Kingdom, in England. This is why I speak English, that's all. And that is why I like English. It's nice to speak. Anyway, I am a theoretical physicist, okay? My research is in cosmology. Theoretical cosmology, or if you want, astrophysics. It has to do with theoretical physics, okay? And cosmology, what is cosmology? Right? Cosmology is, modern cosmology is that part of physics which tries to understand the evolution and the origin, eventually, of what we call the universe, the cosmos, the universe. Right? Astrophysics is that part of physics which studies the properties of the celestial objects, the heavenly bodies, like they used to say, right? Stars, planet, nebulas, and all sorts of things that are present and that are part of the universe, and so forth. And of course, both subjects are very closely interrelated. They are connected, of course, right? So this is what I had been studying all along and working on. Yes. My specific area, if you want to know what my specific interest is, especially at the moment, it's just one word. It's gravitation. It's just about gravity. There are a lot of theories about gravitation. They are old, probably you've heard about old ideas about gravitation. They are modern ideas. Isaac Newton's universal theory of gravitation, you probably have heard about that somehow. That's a very interesting thing. Extremely beautiful construction. But there is Albert Einstein's general relativity theory, and that's also about gravity. And it's saying something totally different about gravity with respect to the Newtonian framework, Newtonian conceptions. And nowadays, people are changing again something about gravity. Okay, there are big cosmological problems to solve. There's the question of how to unify theories that deal with gravity, like general relativity, and another part of physics, which is called quantum physics. That's another very, very amazingly interesting but puzzling part of modern physics, right? We will speak in the next part in the second part in springtime, I guess, okay, of this year about relativity, a bit about relativity, and a bit about quantum physics, okay? But today, as you have been told, and as you know, I will just give you a general overview, if you don't mind, about electromagnetism, which is a hugely important milestone, like they say in English, a milestone of physics. That's electromagnetism. It's amazingly important. So, that's for today, right? Do you all understand, I mean, not understand in the sense of comprehension, but can you hear me quite clearly, yes? Usually I don't have a good voice. So, it might be useful to change. Oh yes, yes. Well, you see there are a few images, right? A few simple concepts. I mean, this is just to remind us about the very important part of physics which I already mentioned. Isaac Newton, Newtonian physics, in particular Newtonian mechanics, okay? In particular Newtonian gravitation and so forth. Why do I mention this? This Newtonian physics has been and is still, up to some level, extremely successful, right? It's very, very successful, of course. And everything that is contained in one of Newton's main published works, the Principia Mathematica, Philosophiae Naturalis, is containing essentially Newtonian dynamics, Newtonian gravitation, and a few other things. I mean, elements of Newtonian mechanics which enables you to understand, up to some level, a great amount of terrestrial phenomena, okay, mechanical phenomena, which are observable here on Earth, on this planet. But not only that, a huge amount of phenomena are describable, understandable, you could also say compressible to just a few fundamental principles of dynamics and a very interesting idea of Isaac Newton, universal gravitation and so forth, and its mathematical description. So, with this dynamics, not only terrestrial phenomena are understandable, predictable to some extent, but also celestial phenomena, and so celestial mechanics is understandable easily with Newtonian things. All the paths and trajectories of satellites, space shuttles and space things and everything you can imagine is computed today with Newtonian mechanics. Very, very tiny corrections of relativistic ones are needed, but the basic thing is still Newton. And another thing that Newton tried to describe is light. You know about Newton's reflections and thoughts about light, okay? The colors of light, the composition of white light, of all the colors into white light. And also, this is the important thing, what did Isaac Newton think about light, about the essence of light. What is light, according to Isaac Newton? Well, it is essentially reduced again to a mechanical thing. You might say that Newton tried to explain optical phenomena and light with a particle model of light, corpuscles. I mean, what is light according to Isaac Newton? It's a flux of very fast moving, tiny little particles, material particles, particles which have a mass. They are almost point-like, and they are very small, okay? But they move very fast, and Isaac Newton tried to explain all optical phenomena with a mechanistic model of light, okay? And I'm mentioning this to emphasize something. I mean, that everything that emerged out of this Newtonian physics model can be called the mechanistic world view, right? That is, everything, all phenomena, seems to be describable in terms of what? In terms of material objects or particles and forces. Force, the concept of force, and the action of forces onto these material objects. Like gravitation, universal gravitation says that between any two massive objects you have an attractive force, right? There exists, an attractive force, and this gravitational force is an action at a distance. It acts immediately on surrounding objects, material objects. And it has a given mathematical dependence. I mean, the intensity of the force depends on the masses of the object, of course. But it also depends on the distance between the objects, okay? It's, you know, that Newton's law is an inverse square law. We will come back to that very briefly. The intensity of the gravitational attraction between two massive objects is inversely proportional to the square of the distance which the centers of these objects, if these objects are huge or big or something. Right? So the mechanistic worldview corresponds to the union of all these things. Another ingredient is the collision between massive objects, of course, which obeys definite laws. And you add to that the three principles of Newtonian dynamics, right? Remember what dynamics is. Newtonian dynamics is that part of physics which tries to study the effect of the forces on the state of motion of an object, material object, and so forth. So you have Newton's famous second principle of dynamics, the first one which is inertia, property of inertia, and so forth, and the third one, which is the action-reaction principle, which is very important as well. And that sort of, you know, union of these principles allowed, of these few principles, there are 4 or 5 maybe, a few principles allows you to understand and to describe very well an amazingly vast or huge number of mechanical phenomena on Earth, in space, and so forth, so forth, so forth. At the time of Isaac Newton, I mean, this was, of course, a triumph of the mechanistic worldview. Right. Now, let me just proceed with that. It's not moving. Why is it not moving? It is changing. Yes, you can't see very well the right-hand part, but don't worry, this is the sort of main menu, okay, conceptual menu, very summarized, okay, very essential menu of the things I would like to say something about in English. Of course. So what do we have to speak about at least, or what should you remember vaguely maybe, right? When you want to say something about electromagnetism, about its ingredients, about its fundamental properties, about its content, right? You see, the first thing is, I'll say something briefly, and you all probably have heard about static electricity, about magnetism, natural magnetism, the one produced by magnetic rocks, magnets, natural magnets.